Hello, my name is Christopher Skack and I'm the Applications Engineer for the Signal Source product line here at Tektronix. Today I would like to concentrate mostly on creating coherent optical signals for high baud rate type applications. And I'll be showing you how to do compensation on a 32 gigabaud signal, PAM4 type signal. And I'll show you the steps that we go through in order to create this type of signal. For the growing need for faster communication, industry requirements have grown also in the sense that in order to test a transmitter, you need something to verify the transmitter is working properly. So with the AWG series, we can create signals that enable the engineer to validate that the receiver is working properly. And Tektronix has a complete solution from the generator all the way up to the receiver, optical receiver, and an analyzing tool so that you can analyze through the fiber to see what your actual transmit rates are. And with the growing trend towards the long haul type capability through fiber using modulation schemes rather than on-off schemes, we can optimize our high bit rate signals. So we're looking today, I'm going to be able to be creating a 32 gigabaud signal with our AWG70000 series using the 50 gigasample sample rate capability of this box. And we'll also be showing you RFXpress and how to optimize these signals so that you get the best results in the most open eye. We'll be looking at a PAM4 type signal that we'll create using RFXpress.
Before I start the demo, I'd like to go over the specific application that we're going to be generating waveforms for. And this is coherent optical generation. So first of all, let's talk a little bit about some of the capabilities that are built into the AWG70000 series. With this single channel box, we have up to 50 gigasample sample rate and very good fidelity and RF specifications with down to minus 80 dBc spurious free dynamic range, and 10 bits of resolution with around 6 bits of effective number of bits at the 20 gigahertz that we're trying to achieve for these particular signals that we're generating, and the ability to synchronize multiple units, and you'll see why the requirement for this is in future slides. So if we look at a typical system here, this would be a complete system for an IQ-based optical generation and testing all the way up to testing the receiver and the optical links. So in this case, we're using two AWG70000 series 50 gigasample boxes going into a multi-format optical transmitter, the OM5110, then through a fiber length, and then out of the fiber into a signal analyzer, the coherent light wave signal analyzer. And then out of that is electrical signals back into a scope where we have the software running that does the optical modulation analysis software that's part of the OM4106D. So this shows you that we have the complete solution from generation all the way up to analysis. So on the AWG side, there's several different methods. In the last slide I showed you, you could use two AWGs in order to create the IQ. What I call the poor man's method is to use one AWG. It has a differential output, so we use the single-ended outputs to simulate an IQ signal. So here we're going directly into the optical modulator with one channel, and then we put a delay in the other channel, and usually this delay is going to be an integer number of symbol times. So this is again the complete solution, looking a little bit further into it so you can see the connections. And as you see here, we're able to do in this configuration, we're able to do the full duplexing modulation capability. So this gives you the ability to do a complete test with one AWG and the required optical system, and then the analysis tool. So the nice thing about an AWG, and it's very good for this application, is the capability of providing multiple signals creation. And for creating PAM signals or QAM signals, the AWG is perfect for this with its analog output and digital input, and with the effective number of bits, we can create very, very good signals. And then also you can add things to these signals that would represent the channel that you're going through to get to the fiber. And so the AWG gives you a complete system for testing the receivers and also providing clean and dirty signals so that you can test your complete system. The other nice thing is with the AWG in combination with software that's called RFXpress, we have most of the modulation characteristics or schemes provided in the RFX general tool. And this tool allows us to build these modulation scenarios without having to know MATLAB. You can go in and just create these signals. Or if you have a waveform that you've already defined, you can also import that into RFXpress. So on a complete system where you want to do polarization, division multiplex type signals, then a 4-channel system is required. In order to get the full sample rate, we have to synchronize 4 AWGs in order to get the polarizing capability. And we are able to synchronize very well with less than 100 femtoseconds of overall jitter or trigger uncertainty. So this gives you the capability of doing complete signal generation for the polarized division multiplexing scenarios. So again, here's a picture showing the single channel AWG using basically the delay line in the path of one of the outputs so that you can create a simulated IQ type environment. So some of the challenges of using a DAC-based system or an AWG is that DACs tend to have a sin x over x roll-off. All DACs have this characteristic. So in order to create these very complex modulation signals at full amplitude and bandwidth, we have to do some compensation in order to flatten off the characteristic, the bandwidth, in order to give you the full open eye requirement for these type of signals. So we have the capability of creating these waveforms with compensation, and this is basically what the demo will show you when I get to the demo. So to understand this a little bit more, you can see the roll-off, the sin x over x roll-off of the AWG. And in this case, what we're seeing is, minus 20 dB at 20 gigahertz. So most people would think, well, there's no way that we can create a 20 gigahertz signal with the AWG with only 50 gigasamples of sample rate. But with compensation, we can affect this quite a bit. So here is a mathematically compensated sin x over x signal, and you can see now we're looking at around 6 dB down at 20 gigahertz. So this improved it quite a bit, and we can improve it even more with more compensation. So another thing that you need to consider when you're using AWGs, most AWGs, the DACs are around 30, up to maybe 30 gigasamples per second. Ours are 25 gigasamples per second, but we interleave two of them in order to get the full 50 gigasample capability. And this full 50 gigasample capability using interleave actually improves some of the characteristics by enabling a little bit higher amplitude, where we can get 500 millivolts to 1 volt peak to peak on these outputs. And in this slide we see that if you look at the Nyquist, the first Nyquist zone, because we're interleaving, the clock spurs will not be evident because they'll be nulled out, and then any other images coming later after the fundamental, we can filter out using an external filter, and they're fairly low amplitude at this state because of the roll-off of the AWG. But in order to get rid of all of them, you may want to get a filter that basically takes care of the second image there. But this, in effect, gives us the capability of not having to have a reconstruction filter at the end of the DAC, so that we get a much cleaner system, and you don't have to worry about what the reconstruction filter is going to do. You could build your own reconstruction filter in post-process DSP, but we haven't found that that's necessarily required. So here is a particular signal that we're looking at that has been compensated, and you can see that this is a 28 gigabaud signal, and we've got an optical EVM of about 3.7%. So this gives you a good idea of what we can do at the higher baud rates, and what's capable with this setup as far as the AWG70000 series goes. So I talked a little bit about RFXpress, and RFXpress allows us to not only create the waveforms, but then to compensate the waveforms so that we can get the best response. So we get basically full control of the formats, as I said earlier, and the signal rates and the symbol rates, and we can it will automatically compile the waveform and then move it into the AWG so that you don't have to transfer the waveforms manually. This can be run on the AWG, or it can be run on a PC through LAN connection. And the whole process of doing the creation and calibration is very, very fast. We can do a generate and compensation under basically within two minutes. And so this gives you the full capability of doing the calibration, and it does have a wizard in it that takes you through the steps in order to do this calibration. So basically the procedure in order to do this is we create a baseband signal. We could create the one that I'm going to be using for the demo will be a 32 gigabaud at PAM16 or QAM64. Actually, I'm only doing PAM4, so QAM8 or QAM16. So basically what we do in the RFXpress software is we send out a multi-tone signal, create a multi-tone signal, and then send that out to the oscilloscope. And we look at the oscilloscope and look at the roll-off, and then create the correction coefficients, and then we send those back to RFXpress software, and then that coefficient can be used for any calibration or any compilations after that point. So you only need to do it once. So it makes it very quick. Once you've done the compensation once or the calibration once, you're able to use that same coefficient file each time. And then to look at the EVM on the electrical side, you can use Signal View that also runs on the scope, so that you can see the characteristics of the signal, either looking at an open eye or an EVM. This is basically just a the configuration is we're going directly from the AWG to the oscilloscope. So the other benefit of doing it this way is you could put something else in between there. Say you want to include the characteristics of the optical modulator. You could get the S parameters of that and put that into the AWG generation, such that now you have a compensated signal with the transmission modulator as part of the compensation. So this brings up our capability of going from electrical through fiber and then out of fiber into electrical, and actually look at the EVM at the end point rather than right at the beginning. So as I mentioned, the RFXpress software gives you a lot of flexibility, and it's fairly easy to use. And most of the requirements for this particular application are all within the general purpose tool of RFXpress. You don't have to buy any options for that. But like I said, we can build the modulation. We have the base data, PRBS base data capability, and filters. And you can also, if you have a predefined filter that you want to use, you can use a file filter that's defined in RFXpress software, such that you can use your own filter if you want to use a filter that you've created. As I mentioned earlier, being able to use S parameters is a nice feature also, so that you can use the corrections through the transmitter. And we do provide the S parameter file for the optical modulators, such that you can use that S parameter as part of your waveform compilation, and then have a complete waveform that gives you the full compensation. So as we see here, this is the wizard that takes you through the calibration, and you can use either an oscilloscope or a real-time spectrum analyzer in order to do this calibration. So this is typical PAM2 signal with 40 gigabaud after compensation. So you can see we have fairly open eyes here, and it actually looks fairly good for 40 gigabaud, which many people say that we can't do with 50 gigasamples of sample rate, but with optimization it works out very well. And a couple more examples here. We see a 28 gigabaud 16 QAM signal with the EVM down to 5.8, and this is through the whole optical system. So this is not just electrical, this is optical EVM. So it's a very good EVM for going through a complete system. So here you can see 32 gigabaud at 16 QAM, and here we're still seeing 6.5% EVM at the end of the line, and again, very good characteristics for doing this kind of testing. And we've even tried going up to 64 QAM and above, and we're able to still get somewhat open eyes, and we're able to do fairly good testing at the end of the optical link cable fibers. So as far as, I know I'm going through this fairly quickly, but in order to generate clean, coherent signals at these baud rates that's being required is some of the characteristics that you need to look at when you're looking at the generation equipment. Of course, number of channels, or being able to synchronize these channels. The sample rate we talked about. Bandwidth is also a big factor, not only bandwidth but frequency response, and that frequency response will be a combination of the true analog bandwidth and the sample rate. Record length probably isn't as important, but you do need some record length in order to build these waveforms, or so that you can build them effectively. And of course, effective bits is one of the big requirements, so that you have enough signals to do compensation on, because you're always going to have to do some compensation in order to equalize out the sin x over x response and the bandwidth roll-off, depending on what the bandwidth roll-off is. And of course, AWGs is something that Tektronix has been building for quite a while. So we're the DAC that we use in the 70000 series is an in-house DAC that we built. And with the many generations of AWGs, we've learned a lot about building DACs for specifically AWGs. So we've got the process down and very clean results from these DACs. So now we'll go on to actually doing a demo so you can see the step-by-step procedure of building these waveforms. Okay, I'd like to start the actual demo here, and I have RFXpress showing here, and this is basically the setup at default. So this is the generic setup that we have here. As I mentioned in the presentation earlier, we have a lot of capabilities in RFXpress. But first of all, before we start RFXpress or start configuring RFXpress, we need to make sure we're connected to the instruments. So I'm going to go ahead and select my instrument controller here. And I'm connected through LAN to both the AWG and the scope in this case, so I can communicate to both of them. I really only need to communicate at this time to the AWG, and when we do calibration, I'll connect to the scope. So we can go in and identify the instrument to make sure that we are connected. So, and of course the way to connect this is just through the LAN connection. I'm going through a server right now, so there's no issue here at all. So in RFXpress, I'm going to go ahead and use this generic setup here, and I'm going to start off by setting this up for IQ. Now that we're in IQ, I'm going to go ahead and set my base data, and like I said in my presentation, is you can use either our built-in PRBS base data, or you can provide your own pattern or file. So I'm going to go ahead and put this up at, let's go 15 PRBS. And I'm not going to mess with the signal carrier amplitude characteristics. I'm going to go ahead and change this, and as I mentioned, we have a lot of different modulation capability built into RFXpress. And you can also, like I said earlier, use your own files or user-defined files instead of using our modulation schemes. So for this particular demo, I think I'm going to use, let's see here. Let's just do a PAM16 or QAM16, which is PAM4. And I'm going to go ahead and set the symbol rate here to 32 gig. And this works out to 32 gigabaud, basically the same thing. I'll go ahead and use a raised cosine filter, but I'm going to go ahead and change the filter characteristics to 0.2 instead of 0.35, and I'm going to leave the window to none. So now that we've created this particular scenario, we'll go into the compile settings here, and you notice that there's a little tab on the right side here to get into the settings, and then you have a bigger tab that actually does the compilation. So you got to make sure you hit the little tab in order to get to the compilation settings. I'm going to go ahead and make sure this defaults to 10K, and basically when it compiles, it will send the waveform to channel 1 in the AWG. And we're going to go ahead and leave it in IQ, and I'm going to go ahead and take this off automatic. Automatic basically tries to give you oversampling of 6 times. Since we're pushing this to the max, I'm going to just specify 50 gigasamples so that we're using the maximum capability. So right now we don't have any correction files, so I'm going to leave that blank. And normalization, I'm going to leave everything else as default. The nice thing about RFXpress is that it automatically adjusts for the wraparound effect so that when you're repeating a waveform, you don't get any spurs or any characteristics at the beginning and end of the waveform if they because they are matched. And this is one thing that RFXpress takes into consideration. And if you did do this in MATLAB, you'd have to do this on your own. So this is nice to have this built into the application. So I'm going to go ahead and say OK to this. So I'm going to go ahead and compile this. And you see that was very quick. Let's see here. Go ahead. So we've compiled the waveform now. What I'd like to do is now go in the calibration mode. So it's good to always calibrate or compile one waveform prior to doing your calibration. What I'm going to do now is go in and do my calibration. So we're going to go ahead and continue through here. We're going to set the calibration to RF and just leave it in the default state. I'm using an oscilloscope to do my compensation, and so I'll go on next here. So we want to make sure we're connected. We can test the connection here, and it is connected. So we're able to go ahead and start our calibration here. So the way I have it set up, we're at 50 gigasamples. We're going to be using the correction factor in channel 1. We can go up to 10 bits here. I'm going to go ahead and set my maximum frequency or end frequency to 19 gigahertz. And I'll leave the start frequency at 10 megahertz. And you can set a number of iterations to get the best compile or get the best characterization for your compensation by doing several iterations. So I'm just going to go ahead and select 3 here, and I'm going to go ahead and browse for a particular place that I want to put these actual compensation files. So I'm just going to use a temp directory here, so I know where they're at. And so we'll go ahead and save that there. Oh, we're going to put a file name. So we're using 16 quam -32 gigabaud. And go ahead and save it as that. So we're done with this, so we'll go ahead and say next. And of course it gives you a diagram showing you that you need to connect to channel 1 of the oscilloscope, and we are connected here. And so now it's going to go off and do the actual calibration. So basically it's sending a multitone signal to the scope, looking at the amplitude characteristics of that and also the phase relationship, and then compensating or getting the coefficient factors back, and then creating the coefficient and then sending that back to RFXpress in the file that we created, so that we can then use that for all the compilations after. So it's completed now. That was fairly quick, and you can see the characteristics of the compensation. So at the roll off, of course, we're given a little bit of a little bit more amplitude at the specific frequencies where it's rolling off at. So we'll go ahead and finish here. So now we've created a waveform, or created the compensation. So if we go back into the compilation menu, we want to make sure that the correction file is available, and it's the correction file that I specified. So now I'm going to go ahead and do another compilation. I'm not going to change anything here. It automatically set this after it did the calibration. So I'm going to overwrite the signal that I have. So now I've basically done the calibration. I'm going to go ahead and show you this on the AWG scope now, so you can see the actual characteristics of what's going on the scope.
So now I'd like to show you on the actual AWG and scope. So here we're sitting in a default setting. I am running the RFXpress over LAN, so I'm going to go ahead and compile one of the waveform that we created with the compensation. So I'm going to go ahead and compile it here. And you can see that it transferred very quickly, and it's located in channel 1 of the AWG now. When we're doing this IQ type of calibration, we can only do calibration on one channel at a time. So in this case, we're basically showing the Q waveform which was not compensated. So what I want to do is show you in signal view what it looks like, and of course we wouldn't be able to use this waveform too much. So this is an uncompensated waveform directly out of the AWG using the compilation that we created. Now what I'm going to do is drag the actual compensated waveform into channel 1 of the AWG and then capture that on the scope. And you can see now that we do have fairly good open eyes with the 32 gigabaud waveform that we've created from the AWG and displayed it here on the scope. And so this is a good example of how quickly and easily it is to create these complex waveforms for coherent optical applications. And hopefully this will clear up some questions of whether the 50 gigasamples is enough to do compensate or enough to do this coherent optical. And as you saw in my presentation, we've been able to take this up to much higher compilation or much higher QAM rates and baud rates.